Hello there, and welcome to the Sleepy Library. Tonight, we are going on a gentle journey downward, not into sleep just yet, but into the earth itself. A journey to discover what lies beneath the ground you stand on every single day. We will explore the hidden world that exists miles below your feet, a world of immense heat, flowing rock and swirling metal. A world that shapes everything above it, from the mountains that rise toward the sky to the magnetic shield that protects us from space. This is not a frightening journey. It is a wonder-filled one. So settle in, let your shoulders drop, and allow your mind to wander downward with me into the beautiful mystery of our planet's interior. For most of human history, the interior of the Earth has been a mystery wrapped in darkness. Ancient peoples imagined hollow chambers filled with fire, or vast underground oceans, or even entire civilizations living in the depths. These stories, while beautiful in their imagination, were far from the truth. But they reflected something fundamental about the human spirit. Our desire to understand what lies hidden, to know what exists beyond the reach of our eyes and hands. Today, through the careful work of scientists over many generations, we can finally answer some of these ancient questions. We know what lies below. And what we have discovered is more extraordinary than any myth or legend. Before we begin our descent, take a moment to feel the ground beneath you. If you are lying in bed, feel the mattress, the floor below it, the foundation of the building, and the solid earth that supports it all. If you are sitting, imagine your weight pressing down through the chair, through the floor, down into the soil and rock below. That ground feels permanent and unchanging, as solid and reliable as anything in your life. And yet, if you could see through it, if you could peer down with some magical vision that penetrates rock and metal, you would see a world in constant motion. You would see layers of stone flowing like thick syrup. You would see oceans of molten metal swirling in currents driven by heat and rotation. You would see a planet that is alive, not with consciousness, but with energy and movement and endless change. This is what we will discover tonight. Not through digging or drilling, but through understanding. Through the patient work of science, which has given us eyes to see into places no human will ever physically visit. Let us begin. Imagine holding an apple in your hand. Notice how thin the skin is compared to the fruit beneath. The earth is much the same. The ground we walk on, the crust, is astonishingly thin when you consider the vastness of what lies below. If earth were an apple, the crust would be no thicker than the peel. Everything we have ever known, every city, every ocean, every mountain range, exists on this delicate outer shell. The crust comes in two varieties. There is continental crust, which makes up the land masses where we build our homes and grow our crops. This crust is thicker and composed mostly of granite, a light-colored rock rich in silicon and aluminium. Continental crust can be as much as 44 miles thick in some places, particularly beneath tall mountain ranges. Then there is oceanic crust, which forms the floor of the oceans. This crust is much thinner, only about 3 to 5 miles thick, and it is made of darker, denser rock called basalt. The salt is rich in iron and magnesium, which makes it heavier than granite. Because of this difference in density, the continents sit higher, like wooden blocks floating on water, while the ocean floors sink lower. The crust is solid and brittle. It breaks rather than bends. When forces push against it, it cracks and fractures, creating the faults and earthquakes we experience at the surface. But for all its seeming permanence, the crust is just the beginning. Below it lies something far more vast and far more powerful. Think about what the crust means for life. Everything we know, everything we have ever experienced, has happened on or within this thin shell. Every mountain ever climbed exists within the crust. Every ocean, no matter how deep, sits atop it. The deepest mine ever dug, the Umponeng gold mine in South Africa, reaches down about 2.5 miles. That sounds impressive until you realize it has barely scratched the surface. If the crust were a mile thick, that mine would reach less than halfway through. But the crust is much thicker than a mile in most places, so even our deepest excavations have only nibbled at the very top of it. The rocks of the crust are relatively cool, at least compared to what lies below. Near the surface, temperatures are moderate, shaped more by the sun and seasons than by the Earth's internal heat. But as you descend, even within the crust, the temperature rises. This increase follows what scientists call the geothermal gradient. In most places, the temperature increases by about 70 to 90 degrees Fahrenheit for every mile you go down. So, at a depth of 3 miles, deep within a mine or borehole, the rock might be 150 to 200 degrees Fahrenheit, hot enough to burn your hand. At the bottom of the crust, temperatures can reach 1,300 degrees Fahrenheit or more, hot enough to glow if you could somehow see it. The composition of the crust varies from place to place. Beneath your feet right now, depending on where you are, there might be sandstone formed from ancient beaches, limestone made from the shells of countless sea creatures, granite pushed up from deep magma chambers, or basalt erupted from undersea volcanoes millions of years ago. Each type of rock tells a story about how it formed, about the conditions that existed when it crystallized, or compacted, or metamorphosed. The crust is not just a layer, it is a library, a record of Earth's history written in stone, preserving evidence of ancient oceans, vanished mountain ranges, and climates long past. Just beneath the crust begins the mantle, and the mantle is where things become truly extraordinary. The mantle extends downward for about 1,800 miles, making up more than 80% of Earth's total volume. To give you a sense of scale, if you could somehow stand at the bottom of the mantle and look up toward the surface, you would be looking up through a distance roughly equivalent to flying from New York to Australia. The mantle is not made of the same light rocks as the crust. It is composed of heavier, iron-rich minerals like olivine and pyroxene. These minerals give the mantle its greenish-brown color when we see samples brought to the surface by volcanic eruptions. The mantle is solid rock, but it is not rigid like the crust above it. Because of the immense heat and pressure deep within the Earth, the mantle behaves more like thick honey or bread dough. It flows, but incredibly slowly, moving just a few centimeters each year. This movement, called convection, is what drives the motion of the tectonic plates at the surface. Think of it as a very slow, very thick river of rock, circulating heat from the depths toward the surface over millions of years. To understand how rock can flow, imagine honey on a cold day. If you try to pour it quickly, it seems solid, resisting your efforts. But if you leave it alone and wait patiently, it will slowly spread and flow, moving under its own weight. The mantle is similar, except instead of minutes or hours, the motion takes thousands or millions of years. The rock is hot enough and under enough pressure that its crystal structure can deform very slowly. Individual atoms can migrate through the crystal lattice, allowing the entire mass to change shape without ever melting. This process is called creep, and it is how solid rock can flow. The convection patterns in the mantle are complex and three-dimensional. Hot material rises from near the core mantle boundary, slowly ascending over millions of years. As it rises, it cools slightly by transferring heat to the surrounding rock. Eventually, it reaches the top of the mantle, where it spreads out horizontally beneath the lithosphere, pushing the tectonic plates around like rafts on a sluggish current. Then, having cooled, the material becomes denser and begins to sink back down. This creates massive circulation patterns, loops of rising and falling rock that cycle heat from the deep interior to the surface and back again. Imagine you could somehow mark a single piece of rock in the mantle and follow its journey. It might start near the core, heated by the warmth radiating from below. Over millions of years, it would rise, ascending through hundreds of miles of mantle, gradually cooling as it goes. When it reached the top, it might spread sideways for a few hundred miles before cooling enough to sink. Then it would descend, falling slowly back into the depths, taking millions more years to return to where it started. The entire cycle, from bottom to top and back again, might take 200 million years or more. That is longer than the time since the appearance of the first mammals on Earth. The uppermost part of the mantle, just below the crust, is cooler and more rigid. This rigid upper mantle sticks to the bottom of the crust, and together they form a layer called the lithosphere. The lithosphere is broken into large pieces, the tectonic plates, which float atop the softer, more fluid part of the mantle below. This softer zone is called the asthenosphere, which means weak sphere. The asthenosphere is weak because it contains tiny amounts of melted rock dispersed through the otherwise solid material. This slight amount of melt makes the asthenosphere slippery and allows the tectonic plates above to slide around. Without this weak zone, the continents would be locked in place, unable to move as they have throughout Earth's history. As you descend deeper into the mantle, the pressure increases. The weight of all the rock above presses down, squeezing the minerals into new, denser forms. Around 400 miles down, the minerals transform into structures that can withstand the higher pressure. Around 410 miles deep, there is a noticeable change, a discontinuity where seismic waves suddenly speed up because the rock has rearranged itself into a more compact form. This is called the transition zone. Even deeper, at about 410 miles, another transformation occurs, marking the boundary between the upper and lower mantle. The lower mantle is even more dense and hot. Temperatures here can reach 3,000 degrees Fahrenheit or more. Despite the heat, the rock remains solid because the pressure is so immense that it cannot melt. It is a strange place, this lower mantle, where the rules of the surface world no longer apply. Here, pressure keeps things solid, even when temperatures would normally turn them to liquid. Near the very bottom of the mantle, about 200 miles above the core, lies one of the most mysterious regions in all of Earth's interior. Scientists call it the D-double prime layer, and it is a zone where seismic waves slow down dramatically. No one is entirely sure what makes this layer so unusual. Some think it may be a graveyard of ancient tectonic plates that sank down from the surface long ago and accumulated at the bottom of the mantle. Others believe it might be pockets of partially melted rock, or areas where the composition is simply different from the rest of the mantle. Whatever it is, the D-double prime layer acts as a boundary, a transition zone between the solid mantle and the liquid metal core below. And now we arrive at the core, the heart of our planet. The core is split into two distinct regions, the outer core and the inner core. The outer core is a sea of liquid metal, mostly iron and nickel, with traces of lighter elements like sulfur, oxygen, silicon mixed in. This liquid layer is about 1,400 miles thick and incredibly hot, with temperatures ranging from about 8,000 to 10,000 degrees Fahrenheit. The metal here is not just sitting still. It churns and swirls, driven by heat rising from the even hotter inner core below. The outer core is a strange and violent place, though we will never witness it directly. The liquid metal moves in complex patterns, driven by the heat escaping from the inner core and by the rotation of the entire planet. The Coriolis effect, the same force that causes hurricanes to spin, organizes the flow into spiraling columns aligned roughly with Earth's axis of rotation. These columns of flowing metal can be hundreds of miles wide and stretch from the top of the outer core to the bottom. They twist and merge and split apart, creating a constantly changing pattern of motion that has continued for billions of years. The pressure in the outer core is immense, more than 1 million times the atmospheric pressure at the surface. Under such conditions, the properties of matter change. The liquid iron is far denser than any liquid you have ever encountered. It is also an excellent conductor of electricity, which is crucial for generating Earth's magnetic field. The combination of a rotating, electrically conductive fluid creates the perfect conditions for the geodynamo, the process that sustains the magnetic field over geological time. This motion of liquid metal is what generates Earth's magnetic field. As the molten iron moves, it creates electric currents, and these electric currents produce magnetic fields. The magnetic fields, in turn, influence the motion of the metal, creating a feedback loop that sustains the field over time. This process is called the geodynamo, and it has been operating for billions of years. The magnetic field it produces extends far out into space, forming an invisible shield around our planet called the magnetosphere. This shield deflects harmful solar wind and cosmic radiation, protecting the atmosphere and making life on Earth's surface possible. Scientists have created computer simulations of the geodynamo, using powerful supercomputers to model the complex flow of metal in the outer core. These simulations show that the magnetic field is not static. It changes over time, with the strength and orientation varying on timescales of years to millions of years. Sometimes the field weakens, sometimes it strengthens, and occasionally, over periods of hundreds of thousands of years, it reverses completely, with the magnetic north and south poles switching places. These reversals are a normal part of Earth's magnetic behavior, driven by the chaotic nature of the convection in the outer core. At the very center of the Earth lies the inner core, a solid ball of iron and nickel, about 1,500 miles across. That is roughly the size of our moon. The inner core is unimaginably hot, with temperatures reaching more than 9,000 degrees Fahrenheit. At this temperature, iron should be liquid, but the pressure at the center of the Earth is so extreme, more than 3 million times the pressure at the surface, that it squeezes the metal into a solid state. The atoms are packed so tightly together that they cannot move freely, even though they vibrate with intense heat. The inner core spins slightly faster than the rest of the planet, completing one extra rotation about every 1,000 years. It is a world unto itself, isolated by the liquid outer core, unreachable by any drill or probe we could ever build. And yet, we know it is there. We can detect it through the way seismic waves travel through the Earth. The inner core is a silent giant, hidden at the center of everything, holding the memory of Earth's formation in its crystalline structure. The discovery of the inner core is one of the great detective stories of science. For many years, scientists knew that the Earth had a core made of metal, but they thought it was entirely liquid. Then, in 1936, a Danish seismologist named Inga Lehmann was studying seismic waves from earthquakes when she noticed something unusual. Some waves that should have been completely blocked by the liquid core were instead appearing on the opposite side of the Earth, but in unexpected places. She realized that these waves must be passing through something solid deep within the core, something that bent the waves in a different way than the liquid metal around it. This solid region, she concluded, must be the inner core. Her discovery revolutionized our understanding of Earth's interior and earned her recognition as one of the pioneering seismologists of the 20th century. The inner core is not perfectly smooth and uniform. Studies using seismic waves have revealed that it has structure, with seismic waves traveling faster through it in some directions than others. This suggests that the iron crystals in the inner core are aligned in a particular orientation, possibly due to the rotation and magnetic field of the Earth. Some scientists even think the inner core might be rotating at a slightly different speed than previously thought, or that it might have its own internal structure, with layers or regions of different composition. The inner core grows very slowly over time. As the Earth cools, heat escapes from the core, and some of the liquid iron in the outer core freezes onto the surface of the inner core. This process releases latent heat, the energy that is released when a liquid solidifies, and this heat helps drive the convection in the outer core that powers the geodynamo. In this way, the growth of the inner core is intimately connected to the existence of Earth's magnetic field. Without the slow crystallization of iron onto the inner core, the convection might weaken, and the magnetic field might eventually fade away. The Earth is warm, not just at the surface where the sun shines, but deep, inside where no sunlight has ever reached. The heat within our planet has been there for more than 4.5 billion years, and it continues to flow outward, shaping the geology we see above. But where does all this heat come from? Why is the inside of the Earth still so hot after all this time? The answer lies in two main sources: primordial heat and radiogenic heat. Both contribute roughly equal amounts to the total heat budget of the planet. Primordial heat is the leftover warmth from Earth's formation. When our planet was born, it formed through a process called accretion. Small particles of dust and rock in the early solar system collided and stuck together, gradually building up larger and larger bodies. Each collision released energy, and as Earth grew, these impacts became more violent. The kinetic energy of these collisions was converted into heat. By the time Earth reached its current size, it was a molten ball of rock and metal, glowing with the heat of its own creation. As the planet cooled, the heavier elements, like iron and nickel, sank toward the center, forming the core. This process, called differentiation, released even more heat. The gravitational potential energy of the sinking material was transformed into thermal energy, heating the interior even further. All of this heat from the early days of Earth's formation is still trapped inside the planet. Because rock is a poor conductor of heat, it takes an incredibly long time for this warmth to escape to the surface. Even after billions of years, a significant amount of primordial heat remains in the deep interior. The second source of heat is radioactive decay. Deep within the mantle and crust, there are small amounts of radioactive elements like uranium, thorium, and potassium. These elements are unstable. Over time, their atomic nuclei spontaneously break apart, releasing energy in the form of radiation. This process is called radioactive decay, and it generates a tremendous amount of heat. Uranium-238, thorium-232, and potassium-40 are the primary contributors. As their nuclei disintegrate, they emit particles and energy that are absorbed by the surrounding rock, warming it from within. This heat is constantly being produced, even today, and it will continue for billions of years into the future, because the half-lives of these elements are extraordinarily long. The half-life of uranium-238, for example, is about 4.5 billion years, roughly the age of the Earth itself. The process of radioactive decay is fascinating when you consider it in detail. Each radioactive atom is like a tiny clock, ticking away until the moment it decays. But we cannot predict when any individual atom will decay. It might happen in the next second, or it might not happen for billions of years. Radioactive decay is a fundamentally random process, governed by the strange rules of quantum mechanics. However, when you have trillions upon trillions of atoms, the randomness averages out, and the overall rate of decay becomes very predictable. This predictability allows scientists to use radioactive elements not only to understand Earth's heat budget, but also to date rocks and determine the age of geological formations. When uranium decays, it does not simply vanish. It transforms into a different element, releasing energy in the process. Uranium-238 decays through a long series of steps, passing through various intermediate elements like thorium, radium, and radon, before eventually becoming stable lead. Each step in this decay chain releases a small amount of energy, and all of these tiny releases add up to a substantial amount of heat. The same is true for thorium and potassium. Together, these three elements and their decay chains produce about 20 terawatts of heat, which is roughly half of the total heat flow from Earth's interior. Scientists estimate that about half of the heat escaping from Earth's interior comes from this radiogenic source, while the other half comes from the primordial heat left over from the planet's formation. Together, these two sources produce about 47 terawatts of heat, which flows continuously from the interior to the surface. To put that in perspective, 47 terawatts is more than double humanity's total energy consumption from all sources combined. It is an immense amount of energy, quietly radiating from beneath our feet every moment of every day. But there is another factor that amplifies the heat deep inside the Earth: pressure. As you go deeper, the weight of all the rock above creates enormous pressure. Pressure has a curious effect on matter. It raises the melting point of substances, which is why the inner core remains solid despite its extreme temperature. But pressure also generates heat on its own. When materials are compressed, the molecules are forced closer together, and this compression increases the internal energy, raising the temperature. So, the deeper you go, the hotter it gets, not only because of primordial and radiogenic heat, but also because the pressure itself contributes to the warmth. This combination of heat and pressure creates a dynamic, ever-changing interior. The mantle convects, with hot material rising toward the surface and cooler material sinking back down. The outer core churns, generating the magnetic field. The entire planet is a heat engine, slowly releasing the energy accumulated over billions of years. And this process will continue for billions more. Earth is not a cold, lifeless rock. It is a living, breathing system, warm and active, driven by forces that have been at work since the very beginning. If the Earth's interior is so deeply hidden, how do we ever catch a glimpse of what lies below? One of the most dramatic ways the planet reveals its inner workings is through volcanoes. Volcanoes are, in a sense, windows into the Earth. They bring material from deep within the mantle to the surface, allowing us to see and study rocks that would otherwise remain forever out of reach. Magma, the molten rock that erupts from volcanoes, forms in the mantle. The mantle is solid, but under certain conditions, small amounts of it can melt. This happens most commonly in places where the pressure drops suddenly, or where water and other chemicals lower the melting point of the rock. One of the most active places for magma formation is at mid-ocean ridges, where tectonic plates are pulling apart. As the plates separate, the pressure on the mantle below decreases, and the rock begins to melt. The molten material rises to fill the gap, creating new oceanic crust as it cools. The process of melting rock in the mantle is not as simple as heating ice until it becomes water. Rock is made of multiple minerals, each with its own melting point. When the mantle begins to melt, only certain minerals melt first, while others remain solid. This partial melting creates magma that has a different composition than the original rock. The magma that forms is usually richer in silicon and lighter elements, which makes it less dense than the surrounding solid rock. This lower density causes the magma to rise, slowly working its way upward through cracks and weaknesses in the overlying rock. As magma rises, it can change composition further. It might incorporate pieces of the rock it passes through, dissolving some minerals and adding them to the melt. It might cool slightly, causing some minerals to crystallize out and sink, leaving the remaining liquid with a different composition. By the time magma reaches the surface and erupts from a volcano, it may be very different from the material that first melted deep in the mantle. Another common setting for magma formation is at subduction zones, where one tectonic plate slides beneath another. As the descending plate sinks into the mantle, it carries water trapped in its minerals down with it. This water is released as the plate heats up, and it lowers the melting point of the surrounding mantle rock. The result is the formation of magma, which rises toward the surface and often erupts violently, creating volcanic arcs like the ones found around the Pacific Ocean. The Pacific Ring of Fire is one of the most active volcanic regions on Earth. It is a horseshoe-shaped belt of volcanoes and earthquake zones that circles the Pacific Ocean. The reason for all this activity is simple. The Ring of Fire is where several tectonic plates meet and interact. Plates are colliding, sliding past each other, and diving beneath one another, creating the perfect conditions for magma generation and volcanic eruptions. More than 75% of the world's volcanoes are located in this region, and it is also where 90% of the world's earthquakes occur. But not all volcanoes are found at plate boundaries. Some, like the volcanoes in Hawaii, are located in the middle of tectonic plates, far from any edges. These volcanoes are fed by mantle plumes, which are columns of hot rock rising from deep within the mantle, possibly even from near the core mantle boundary. A mantle plume is like a vertical river of heat, carrying warmth from the deep interior to the surface. As the plume reaches the lithosphere, the pressure drop causes the rock to melt, forming magma that eventually erupts as a volcano. The Hawaiian Islands were formed by a plume that has been active for millions of years. As the Pacific Plate moves over the stationary plume, new volcanoes are created, forming a chain of islands that traces the plate's motion across the ocean. Volcanic eruptions, while often seen as violent and destructive, are simply the Earth's way of releasing heat and pressure from below. The magma that reaches the surface carries with it clues about the composition and conditions of the deep mantle. By analyzing volcanic rocks, Scientists can learn about the chemistry, temperature, and even the age of the material from which they formed. In this way, volcanoes are not just windows. They are messengers, bringing us information from a world we can never visit. Some volcanoes are so powerful that they have shaped entire climates and reshaped continents. These are called supervolcanoes, and they are among the most formidable natural events on Earth. A supervolcano is not a single mountain. It is a massive volcanic system capable of ejecting more than 240 cubic miles of material in a single outburst. To put that in perspective, that is enough ash and rock to bury an entire state under several feet of debris. The most famous supervolcano in the United States is Yellowstone. Beneath the serene landscape of Yellowstone National Park lies a vast chamber of magma, several miles across and extending deep into the crust. This chamber has erupted 3 times in the past 2 million years, with the most recent major eruption occurring about 640,000 years ago. When Yellowstone erupts, it does not build a towering cone like Mount St. Helens or Mount Fuji. Instead, the ground collapses inward, forming a giant crater called a caldera. The eruption sends ash high into the atmosphere, where it can spread across entire continents, blocking sunlight and cooling the climate for years. But supervolcanoes are rare, and the intervals between their eruptions are measured in hundreds of thousands of years. There is no need to fear them on a human timescale. They are simply another reminder of the immense power stored beneath the surface, a power that has been shaping the planet for billions of years, and will continue to do so long after we are gone. Volcanoes, in their own way, are how the Earth breathes. They release gases that were trapped in the mantle, including water vapor, carbon dioxide, and sulfur compounds. Over Earth's history, volcanic outgassing has played a crucial role forming the atmosphere and the oceans. The water in today's oceans, the air we breathe, even the fertile soil that supports plant life, all have their origins, at least in part, in the gases released by ancient volcanoes. So when you see a volcano, do not think of it only as a source of change. Think of it as a connection, a living link between the hidden depths and the world we inhabit. Since we cannot travel to the center of the Earth, how do scientists know what lies beneath? The answer is both elegant and ingenious. They listen, not with their ears, but with instruments that detect vibrations traveling through the planet. These vibrations are called seismic waves, and they are created every time an earthquake occurs. When an earthquake happens, rocks along a fault line suddenly break and shift, releasing energy. This energy radiates outward in the form of waves, much like ripples spreading across the surface of a pond when you drop a stone into the water. Seismic waves travel through the Earth's interior, and by measuring how they move, scientists can infer what they are traveling through. It is like using sound to understand the shape of a room. If you clap your hands in a large cathedral, the echo tells you something about the size and structure of the space. Seismic waves do the same for the Earth. There are 2 main types of seismic waves that travel through the Earth's interior: P waves and S waves. P waves, or primary waves, are compression waves. They move by alternately squeezing and stretching the material they pass through, much like sound waves move through air. P waves are the fastest seismic waves, traveling at speeds of about 4 to 7 miles per second, and they can move through any material, whether solid, liquid, or gas. S waves, or secondary waves, are shear waves. They move by shaking the ground up and down or side to side, perpendicular to the direction they are traveling. S waves are slower than P waves, traveling at about 2 to 3 miles per second. But here is the key detail. S waves can only travel through solid materials. They cannot pass through liquids. This simple fact is one of the most important clues scientists have used to understand Earth's interior structure. Seismometers, the instruments that detect these waves, are placed all over the world. When an earthquake occurs, seismic waves spread out in all directions. Some travel along the surface, causing the shaking we feel. Others dive deep into the earth, traveling through the mantle and core before emerging on the opposite side of the planet. By carefully measuring when the waves arrive at different seismometer stations, scientists can calculate how fast the waves were traveling and what path they took. Here is where things get interesting. Seismic waves change speed when they pass through different materials. They travel faster through denser, more rigid rock, and slower through softer, less dense material. So by mapping the speed of seismic waves at different depths, scientists can identify boundaries between different layers of the Earth. These boundaries are called seismic discontinuities. Think of it this way. Imagine you are in a dark room and you want to know the layout of the furniture without turning on the lights. You could clap your hands and listen to the echoes. The echoes would arrive at different times, depending on how far away the walls and furniture are, and the quality of the echo would tell you something about what it bounced off of. A hard wall produces a sharp echo. A soft couch produces a muffled one. Seismic waves work the same way. They bounce off boundaries inside the Earth, and by analyzing these echoes, scientists can map the interior. The speed of seismic waves also tells us about the physical state of the material they are passing through. In solid rock, both P waves and S waves can travel, but in liquid, only P waves can pass through. S waves require the material to have rigidity, the ability to resist shearing forces. Liquids have no rigidity, so they cannot transmit S waves. This simple fact has been one of the most powerful tools for understanding Earth's interior. When scientists observed that S waves disappeared at a certain depth, they knew immediately that they had encountered liquid. That depth, about 1,800 miles down, marks the top of the liquid outer core. The first major discontinuity was discovered in the early 1900s by a Croatian scientist named Andrija Mohorovičić. He noticed that seismic waves from an earthquake sometimes arrived at distant seismometer stations before they arrived at stations closer to the earthquake. This puzzled him until he realized what was happening. The waves that traveled farther had taken a shortcut through the mantle, where they could travel much faster than through the crust. The boundary between the crust and mantle, now called the Mohorovičić discontinuity, or MOHO for short, marks the point where seismic waves suddenly speed up. Further discoveries followed. Scientists found that at a depth of about 1,800 miles, P waves suddenly slowed down dramatically. This marked the boundary between the mantle and the outer core. Even more revealing, S waves disappeared entirely at this depth. Since S waves cannot travel through liquids, this told scientists that the outer core must be liquid. This was a groundbreaking discovery, made not by drilling or direct observation, but simply by listening to how seismic waves behaved. Later, scientists detected that deep within the core, P waves sped up again. This indicated another boundary, this time between the liquid outer core and the solid inner core. The discovery of the inner core was made in 1936 by a Danish seismologist named Inge Lehmann, who carefully analyzed the way seismic waves reflected and refracted within the deep interior. Today, seismic waves are used to create detailed three-dimensional maps of Earth's interior. By combining data from thousands of earthquakes and seismometer stations, scientists can visualize the structure of the mantle and core with remarkable precision. They can identify regions where the mantle is hotter or cooler, where tectonic plates are sinking back down into the depths and where plumes of hot rock are rising toward the surface. This technique, called seismic tomography, is like taking an X-ray of the entire planet. And there are other ways seismic waves reveal secrets. The Earth is constantly humming, even when there are no earthquakes. This low, persistent vibration, called Earth's hum, is caused by ocean waves, atmospheric pressure changes, and the constant movement of the planet itself. Scientists can detect this hum and use it to study the deep interior, much like a doctor listens to a heartbeat to understand the health of a patient. In this way, seismic waves are not just a tool for studying earthquakes, they are a window into the living, breathing interior of our planet. High above your head, invisible to the eye, is a protective shield that wraps around the entire planet. This shield is not made of metal or fabric. It is made of magnetism. Earth's magnetic field extends far out into space, forming a region called the magnetosphere, and it is one of the most important reasons life can exist on the surface. The source of this magnetic field lies deep within the Earth, in the churning liquid metal of the outer core. As we learned earlier, the outer core is composed mostly of molten iron and nickel, and it is in constant motion. This motion is driven by heat escaping from the inner core and by the forces created as Earth rotates. The combination of a rotating, electrically conductive fluid creates what scientists call a geodynamo. The process works like this. As the molten iron flows through an existing magnetic field, it generates electric currents. These electric currents, in turn, produce their own magnetic fields. The new magnetic fields interact with the fluid motion, amplifying the currents and reinforcing the magnetic field. It is a self-sustaining cycle, a feedback loop that has been running for more than 3 billion years. Earth's magnetic field is shaped like a bar magnet, with field lines emerging near the magnetic South Pole in the Antarctic and looping around the planet to re-enter near the magnetic North Pole in the Arctic. The field extends thousands of miles into space, far beyond the atmosphere. On the side of Earth facing the Sun, the magnetic field is compressed by the solar wind, a stream of charged particles flowing outward from the Sun. On the night side, the field is stretched into a long tail that extends millions of miles into space. This magnetic field acts as a shield, deflecting most of the charged particles from the solar wind before they can reach the atmosphere. Without this protection, the solar wind would gradually strip away the atmosphere, much as it has done on Mars, which lost its magnetic field billions of years ago. On Earth, the magnetosphere keeps the atmosphere intact, allowing water to remain liquid on the surface and providing a stable environment for life to flourish. But the magnetic field does more than just protect. It also creates one of the most beautiful natural phenomena on Earth, the auroras. When charged particles from the solar wind do manage to penetrate the magnetosphere, they are guided along the magnetic field lines toward the poles. As they collide with atoms and molecules in the upper atmosphere, they transfer energy, causing the air to glow in shimmering curtains of green, red, and purple light. The northern lights, or aurora borealis, and the southern lights, or aurora australis, are visible displays of the magnetic field at work, reminding us of the invisible forces that surround our planet. The strength of Earth's magnetic field is measured in units called teslas, or more commonly, microteslas. At the surface, the field strength ranges from about 25 to 65 microteslas, depending on where you are. It is strongest near the poles and weakest near the equator. This may not sound like much, but it is more than enough to deflect the solar wind and protect the atmosphere. Interestingly, the magnetic field is not static. It changes over time. The position of the magnetic poles wanders slowly, shifting by several miles each year. Sometimes the field weakens, sometimes it strengthens, and occasionally, over timescales of hundreds of thousands of years, the field reverses entirely, with the north and south magnetic poles swapping places. These reversals are recorded in rocks that contain magnetic minerals. As lava cools and solidifies, the minerals align with the direction of the magnetic field at that time, preserving a record of the field's orientation. By studying these magnetic signatures in rocks of different ages, scientists have discovered that Earth's magnetic field has reversed many times throughout its history. Why do these reversals happen? The answer is not entirely clear, but it is likely related to the chaotic, turbulent motion of the liquid metal in the outer core. Computer simulations of the geodynamo show that the magnetic field can spontaneously flip when the flow patterns in the core become unstable. During a reversal, the field weakens and becomes disorganized for a few thousand years before reorganizing in the opposite direction. These reversals are a normal part of Earth's magnetic behavior, a reminder that even the planet's deep interior is constantly changing. The geodynamo is a marvel of physics, an example of how simple physical processes, heat, motion, and electromagnetism can combine to create something as complex and enduring as Earth's magnetic field. And it is all happening in a place we will never see, deep beneath our feet, in a sea of molten metal spinning in the dark. When we think of life on Earth, we usually picture the surface. Forests, oceans, grasslands, cities. But life is not confined to the thin layer of air, water, and soil at the surface. Life exists deep underground as well, in places where sunlight never reaches and where the pressure and temperature would seem to make existence impossible. This hidden realm is called the deep biosphere, and it is one of the most surprising discoveries in modern science. Microbes, tiny, single-celled organisms, have been found living in rocks more than 3 miles below the surface. Some of these microbes live in cracks and pores within the rock, feeding on minerals and chemicals dissolved in underground water. Others are found in deep aquifers, vast reservoirs of water trapped beneath the continents and ocean floors. These organisms do not rely on sunlight or photosynthesis for energy. Instead, they extract energy from chemical reactions involving minerals like iron, sulfur, and methane. This process, called chemosynthesis, allows them to survive in complete darkness. The conditions in the deep biosphere are extreme. Temperatures can reach 200 degrees Fahrenheit or more. Pressures are immense. There is little oxygen, and the environment is often acidic or highly alkaline. And yet, life persists. These deep-dwelling microbes are incredibly slow-growing. Some reproduce only once every 1,000 years. They exist in a state of near-suspended animation, their metabolism slowed to a crawl, conserving energy in an environment where resources are scarce. These microbes are not just survivors. They are pioneers, exploiting an ecological niche that was only recently discovered. They feed on hydrogen gas released from chemical reactions between water and certain minerals. They metabolize sulfur compounds. They break down organic molecules that have somehow made their way deep underground. In some cases, they even feed on hydrocarbons, the same compounds that make up oil and natural gas. Some scientists think these deep microbes might actually play a role in the formation of petroleum deposits, altering the chemistry of organic-rich rocks over millions of years. How much life is there in the deep biosphere? Scientists estimate that the total mass of microbes living underground may rival or even exceed the mass of all life on the surface. It is a staggering thought. Beneath every forest, every desert, every ocean. There may be an entire hidden ecosystem thriving in the darkness, feeding on the planet's internal chemistry rather than the energy of the sun. These microbes are not just curiosities, they play an important role in Earth's geochemical cycles. They help break down minerals, releasing nutrients that eventually make their way back to the surface. They influence the chemistry of groundwater, affecting everything from the formation of ore deposits to the quality of drinking water. And they raise intriguing questions about the origins of life. If life can thrive in such extreme environments on Earth, similar organisms exist in the subsurface of other planets or moons. Mars, for example, may have a deep biosphere of its own, hidden in fractures beneath its frozen surface. The icy moons of Jupiter and Saturn, like Europa and Enceladus, have subsurface oceans that may also harbor life. The discovery of the deep biosphere has expanded our understanding of where life can exist and what it needs to survive. It has shown us that life is more resilient and adaptable than we ever imagined. And it reminds us that even in the deepest, darkest places on Earth, there is activity, there is change, and there is life. Step back for a moment and consider the Earth as a whole. It is not a static ball of rock. It is a machine, a heat engine powered by the warmth trapped in its interior and the energy released by radioactive decay. This machine has been running for more than 4.5 billion years, and it shows no signs of stopping. At the heart of this machine is convection, the process by which heat moves from the interior to the surface. In the mantle, hot rock rises toward the crust, cools, and then sinks back down to be reheated. This slow, continuous circulation drives the motion of the tectonic plates at the surface. The plates are fragments of the lithosphere, the rigid outer shell of the Earth, and they move at a rate of just a few centimeters per year. That may not sound like much, but over millions of years it adds up. Continents drift apart. Oceans open and close. Mountain ranges rise and erode away. Plate tectonics is the grand orchestrator of Earth's surface processes. It shapes the geography of the planet, determines where volcanoes and earthquakes occur, and influences the climate by controlling the distribution of land and sea. When two plates collide, one may be forced beneath the other in a process called subduction. The descending plate sinks into the mantle, where it is eventually recycled, its material melted and reincorporated into the convecting mantle. At mid-ocean ridges, plates pull apart and new crust is created as magma rises to fill the gap. The movement of the plates is like a giant puzzle, pieces constantly shifting and rearranging. The Atlantic Ocean is growing wider as the Americas drift away from Europe and Africa, spreading at a rate of about an inch per year. The Pacific Ocean is shrinking as its edges are consumed by subduction zones. India is still pushing into Asia, raising the Himalayas higher with each passing year. The Mediterranean Sea is slowly closing as Africa moves northward toward Europe. Over hundreds of millions of years, the continents have come together and broken apart many times. About 300 million years ago, all of Earth's landmasses were joined in a single supercontinent called Pangaea. Over time, Pangaea broke apart, and the pieces drifted to their current positions. But this is not the end of the story. In the distant future, the continents will come together again, forming a new supercontinent, and the cycle will repeat. Plate tectonics is not just a geological process. It has profound effects on life. The movement of the continents changes ocean currents, which in turn affect the climate. When continents are clustered near the poles, ice sheets can form, leading to ice ages. When continents are spread out, the climate tends to be warmer and more stable. The opening and closing of ocean basins creates barriers and bridges for the migration of species, influencing the evolution and distribution of life. The uplift of mountains affects rainfall patterns, creating wet regions on one side and dry regions on the other. In this way, the Earth's interior is intimately connected to everything that happens at the surface. The heat flowing from below drives the motion of the plates, and the motion of the plates shapes the environment in which life evolves. It is all part of a single, interconnected system, a planetary machine that has been shaping and reshaping the surface for billions of years. Within the Earth, there are layers, and within those layers, there are boundaries. Some of these boundaries are well understood. Others remain mysterious, hidden in the depths, revealed only by subtle changes in the way seismic waves travel. We have already mentioned the moho, the boundary between the crust and the mantle. This is one of the most important discontinuities, marking the transition from the light, brittle rocks of the crust to the denser, more fluid rocks of the mantle. The depth of the moho varies depending on where you are. Beneath the ocean floors, it is just 3 to 6 miles down. Beneath the continents, it can be as deep as 40 miles, especially beneath mountain ranges where the crust is thickest. Deeper in the mantle, there is the transition zone, a region between about 250 and 410 miles depth, where the minerals in the mantle transform into denser structures. The most significant of these transformations occurs at about 410 miles, where the mineral olivine changes into a denser form called wadsleyite. This transformation is driven by the increasing pressure, and it causes seismic waves to speed up suddenly, creating a sharp discontinuity. Another transformation occurs at about 520 miles, where wadsleyite changes into an even denser form called ringwoodite. These transformations are like phase changes, similar to the way water turns into ice when it gets cold enough. At the bottom of the mantle, just above the core, lies the enigmatic D double prime layer. This is one of the least understood regions of the entire planet. Seismic waves slow down dramatically in this layer, and there are strange variations in temperature and composition. Some scientists believe the D double prime layer may be a chemical graveyard, a place where old tectonic plates subducted millions of years ago have accumulated and partially melted. Others think it may be enriched in heavy elements that sank early in Earth's history. Still others propose that it might be where mantle plumes originate, columns of hot rock rising from the very bottom of the mantle to create hotspot volcanoes like those in Hawaii and Iceland. The D double prime layer is a frontier of Earth science, a place where our understanding is still incomplete. It is a reminder that even after centuries of study, the Earth still holds secrets, hidden in places we can only probe indirectly with seismic waves and computer models. Another mysterious boundary is the one between the outer and inner core, discovered by Inga Lehmann in the 1930s. This boundary, called the Lehmann discontinuity, or the inner core boundary, marks the transition from liquid metal to solid metal. The pressure at this depth is so great that the iron and nickel, despite being hotter than the surface of the Sun, are squeezed into a solid state. The inner core is a strange place, a world of extreme conditions where the normal rules of matter do not apply. These boundaries are not just lines on a diagram. They are real physical transitions, places where the properties of the material change abruptly. And by studying them, scientists can learn about the processes that shaped the Earth and continue to shape it today. Each boundary tells a story, a chapter in the long history of our planet. If you could somehow listen to the Earth's interior, what would you hear? It turns out that the planet is not silent. It hums, groans, and even sings, though most of these sounds are far too low in frequency for human ears to detect. One of the most intriguing sounds is the Earth's hum, a continuous, low-frequency vibration that was first detected in the late 1990s. This hum is not caused by earthquakes. It is always present, a background resonance that scientists believe is generated by ocean waves, atmospheric pressure changes, and the constant motion of the planet itself. The frequency of the hum is around 3 to 4 millihertz, which is far below the range of human hearing. But with sensitive instruments, scientists can detect it and use it to study the structure of the deep interior. The hum is like a fingerprint of the Earth, a signature of its internal structure and the forces acting upon it. By analyzing the patterns in the hum, scientists can learn about the properties of the mantle, the core, and even the way seismic waves propagate through the planet. It is a subtle signal, but it carries a wealth of information. Earthquakes, of course, produce much louder sounds. When an earthquake occurs, the energy released creates vibrations that can be converted into sound waves. Researchers have taken recordings of these vibrations and sped them up so that they fall within the range of human hearing. The result is an eerie, otherworldly sound, a deep rumble or a high-pitched screech, depending on the type of seismic waves being recorded. These sounds are not just curiosities. They are data, information about the strength, location, and depth of the earthquake, and they help scientists understand the forces at work beneath the surface. Even the motion of the tectonic plates produces sounds. As plates grind past each other, they generate low-frequency vibrations that can be detected by sensitive instruments. These vibrations, sometimes called slow earthquakes or silent slip events, occur over days or weeks rather than seconds, and they release energy gradually rather than all at once. They are too slow to be felt, but they can be heard if you have the right equipment. And then there are the sounds associated with volcanic activity. Before a volcano erupts, magma moving through cracks and chambers in the crust creates vibrations that can be detected and recorded. These volcanic tremors are a warning sign, an indication that an eruption may be imminent. By listening to these sounds, scientists can monitor active volcanoes and provide early warnings to nearby communities. In a sense, the Earth is constantly talking, telling us about its internal state, its stresses, and its movements. We just need to listen. And with each new recording, each new analysis, we learn a little more about the hidden world beneath our feet. For as long as humans have wondered about the Earth's interior, they have dreamed of drilling down to see what lies below. In the late 1950s and early 1960s, both the United States and the Soviet Union launched ambitious projects to drill as deep as possible into the crust. These efforts were part of a larger competition, a race not upward to space, but downward into the Earth. The American project, called Project Mohole, aimed to drill through the oceanic crust to reach the mantle. The project succeeded in drilling a test hole in deep water off the coast of Mexico, but it was cancelled in 1966 due to budget problems and disagreements about its scientific goals. Despite its early promise, Project Mohole never achieved its ultimate aim. The Soviet project, on the other hand, was more successful. In 1970, Soviet scientists began drilling on the Kola Peninsula, near the border with Norway. The goal was to drill as deep as possible into the continental crust, penetrating ancient rocks and studying their composition, temperature, and structure. The project, known as the Kola Superdeep Borehole, continued for more than 20 years. The Kola borehole reached a depth of about 7.5 miles, or 12 kilometers, in 1989. This made it the deepest hole ever drilled into the earth, a record that still stands today. The hole is only about 9 inches in diameter, but it required the invention of new drilling techniques and equipment. Unlike traditional oil drilling, where the entire drill pipe is rotated, the Kohler project used a system where only the drill bit at the tip rotated, reducing the torque on the long string of pipe. The drilling process was slow and difficult. The drill bit had to be pulled out frequently to be replaced or repaired. Each time the bit was pulled out, it took weeks to lower it back down to the bottom of the hole. The deeper they went, the more challenges they faced. The rock became harder and more abrasive, wearing down drill bits faster. The temperature increased more rapidly than expected, causing equipment failures, and the rock itself began to behave strangely, flowing back into the hole like thick paste, requiring constant attention to keep the borehole open. As the drill descended, the scientists made numerous surprising discoveries. They expected to find a layer of basalt at a depth of about 4 miles, a transition known as the Conrad discontinuity. But the basalt never appeared. The rocks at depth were different from what seismic data had suggested, a reminder that seismic waves do not always tell the whole story. The temperature at the bottom of the hole was also much higher than expected, reaching about 356 degrees Fahrenheit instead of the predicted 212 degrees. The intense heat made the rock behave more like plastic than solid material, and it became increasingly difficult to keep the borehole open. The rock would flow back into the hole, requiring the drill to be pulled out and started again. The high temperatures were a major problem. At those temperatures, the rock loses much of its strength and begins to flow under its own weight. The borehole would deform, the walls pressing inward, narrowing the hole and sometimes trapping the drill string. The drilling mud, which was pumped down the hole to cool the bit and carry away rock chips, would break down chemically in the heat, losing its effectiveness. The metal of the drill pipe and bit would soften and deform. Despite all these challenges, the team persisted, developing new techniques and materials to cope with the extreme conditions. The Kohler project also discovered water at great depths, something that was not expected. This water was not in liquid form as we know it. It was trapped within the crystal structure of the minerals, locked in as hydrogen and oxygen atoms. When the drilling process fractured the rock, the trapped gases were released, and they combined to form water. The discovery suggested that vast amounts of water may be hidden deep within the Earth's crust and mantle, stored in a form we are only beginning to understand. Perhaps the most intriguing discovery was the presence of fossils. At a depth of about 4 miles, scientists found microscopic fossils of plankton, tiny organisms that lived more than 2 billion years ago. These fossils were preserved in organic compounds that had somehow survived the immense pressure and heat of the deep crust. It was a reminder that life on Earth is ancient, and that traces of it can be found in the most unexpected places. The Kohler project ended in 1994, not because the drill reached the mantle, but because funding ran out after the collapse of the Soviet Union. The borehole was sealed, and the site was eventually abandoned. Today, the structure that once stood over the hole is mostly ruins, but the borehole itself remains, a testament to human curiosity and ambition. Even at 7.5 miles, the Kohler borehole penetrated only about 1/3 of the way through the continental crust. The mantle, which begins at a depth of about 25 to 40 miles beneath the continents, remained out of reach. And the core, nearly 2,000 miles below the surface, is utterly beyond the reach of any drill we could ever build. Why is it so difficult to drill deep into the Earth? The answer is heat. As you go deeper, the temperature increases at a rate of about 70 to 90 degrees Fahrenheit for every mile of depth. This heat softens the rock, making it flow like putty, and it damages the drill bits and pipes. There is also the problem of pressure. The deeper you go, the greater the weight of the rock above, and this pressure can crush equipment and close up the borehole. And finally, there is the sheer logistical challenge of drilling such a deep hole. The drill string becomes so long and heavy that it is difficult to control, and any mistakes can result in the drill getting stuck or breaking off deep underground. For these reasons, we will never drill to the center of the earth. The technology simply does not exist, and it may never exist. But we do not need to drill to learn about the deep interior. Seismic waves, magnetic field measurements, laboratory experiments, and computer models have given us a detailed picture of what lies below, a picture that becomes clearer with each passing year. Still, it is worth imagining what it would be like if we could drill all the way down. Picture an elevator shaft descending through the earth, with stops at each layer. The first few miles would take you through the crust, passing through layers of sedimentary rock, granite, and eventually basalt. The temperature would rise steadily, and the pressure would increase. At a depth of about 25 miles, you would cross the moho and enter the mantle. Here, the rock would be denser and hotter, glowing a dull red in the darkness. The walls of the elevator shaft would shimmer with heat. As you descended deeper into the mantle, the rock would transition through different mineral phases, each denser than the last. At 400 miles down, you would pass through the transition zone, where the minerals transform under the immense pressure. The temperature would now be well over 2,000 degrees Fahrenheit, and the rock would be so hot that it would glow orange. At the bottom of the mantle, nearly 1,800 miles down, you would enter the strange D double prime layer, where the temperature might reach 5,000 degrees Fahrenheit or more. Here, the rock is so hot and dense that it behaves in ways we are only beginning to understand. Then, at a depth of 1,800 miles, you would reach the core mantle boundary. Here, the solid rock of the mantle gives way to liquid metal. The temperature would be around 8,000 degrees Fahrenheit, and the pressure would be more than 1 million times the pressure at the surface. The liquid iron and nickel of the outer core would be churning and swirling, driven by convection and the rotation of the Earth. If you could somehow survive in this environment, you would see currents of molten metal flowing past you, glowing with intense heat. Finally, at a depth of about 3,000 miles, you would reach the inner core. Here, the pressure is so extreme that the metal, despite being hotter than the surface of the sun, is squeezed into a solid state. The temperature might be as high as 9,000 degrees Fahrenheit or more. The inner core is a solid sphere of iron and nickel, spinning slightly faster than the rest of the planet, isolated in its own world of extreme conditions. And there, at the very center of the Earth, your imaginary journey would end. Of course, this journey is purely imaginary. No elevator could survive the heat and pressure. No material we know of could withstand such conditions. But in our minds, we can travel anywhere, even to places that will forever remain beyond our physical reach. And through the power of science, we can understand what lies there, even if we can never see it with our own eyes. As we come to the end of our journey, let us return to where we began, standing on the surface of the Earth, feeling the ground beneath our feet. That ground, as we now know, is just the thin outer shell of something far more vast and complex. Beneath you, the Earth extends downward for nearly 4,000 miles, through layers of rock and metal, through zones of immense heat and pressure, all the way to the solid iron core at the center. This hidden interior is not separate from the world we inhabit. It is connected to it in countless ways. The heat flowing from the deep interior drives the motion of the tectonic plates, shaping the continents and ocean floors. It powers volcanoes, which release gases that become part of the atmosphere. It generates the magnetic field that shields us from the solar wind and makes life on the surface possible. Even the water in the oceans, the minerals in the soil, and the landscapes we see around us are all, in some way, products of the planet's internal processes. The Earth is not a static, unchanging place. It is dynamic, alive in the geological sense, constantly reshaping itself over timescales that dwarf human lifetimes. Mountains rise and are worn away. Continents drift apart and collide. Ocean floors are created and destroyed. And through it all, the heat engine of the Earth continues to run, powered by the warmth left over from the planet's formation and by the energy released from radioactive decay deep within. We live on the surface of this incredible system, benefiting from its stability, its warmth, and its protection. The thin layer of crust we inhabit is a fragile interface between the fiery interior and the cold vacuum of space. It is a place where conditions are just right for liquid water, for a stable climate, for the chemistry of life. And it is all made possible by the processes happening far below, in places we will never see. So, as you rest tonight, let your mind wander downward one last time. Picture the layers beneath you, the crust, the mantle, the core. Picture the slow churning of the mantle, the swirling of liquid metal, the solid sphere of iron at the center. Picture the heat radiating outward, the seismic waves traveling through the depths, the magnetic field lines looping through space. All of it is there, beneath you, supporting you, shaping the world you live in. The Earth is more than just a ball of rock. It is a system, a machine, a living, breathing planet, with a heartbeat measured in the motion of continents and the glow of molten rock. And we are part of that system, living on its surface, connected to its interior in ways we are only beginning to understand. Think about how remarkable it is that we can know these things. We have never seen the core with our own eyes. We have never touched the mantle. We have barely scratched the surface of the crust. And yet, through careful observation, through the patient analysis of seismic waves and magnetic fields, through the study of rocks and minerals, through mathematical models and computer simulations, we have built a detailed picture of the hidden world below. This is the power of science, the ability to understand things that cannot be directly observed, to reach conclusions through reasoning and evidence, to see with the mind what the eyes cannot perceive. And what we have discovered is beautiful. Not beautiful in the way a sunset is beautiful, or a flower, or a piece of music, but beautiful in its complexity, its elegance, its interconnectedness. The Earth is not a random collection of rocks and metal. It is an organized system, shaped by physical laws that we can understand. Heat flows from hot to cold. Dense materials sink, while light materials rise. Rotating fluids generate magnetic fields. Pressure changes the properties of matter. All of these simple principles combine to create the intricate structure we have explored tonight. As you lie here now, preparing to rest, consider your place in this vast system. You are on the surface, the thin boundary between the solid planet below and the empty space above. You are made of atoms that were forged in the cores of ancient stars, scattered through space, and eventually incorporated into the cloud of gas and dust that became our solar system. Some of those atoms were part of the primordial Earth, present at its formation 4.5 billion years ago. Others have cycled through the mantle, been erupted by volcanoes, weathered into soil, absorbed by plants, eaten by animals, and eventually found their way into you. You are, quite literally, made of the earth. Your body is built from the same materials that make up the rocks and minerals below. The iron in your blood once flowed in rivers of molten metal deep in the core. The calcium in your bones was once part of ancient seashells, compressed and heated, and thrust upward to form mountain ranges. You are not separate from the planet. You are part of it, a temporary arrangement of atoms that will one day return to the soil and rock from which they came. But for now, you are here, conscious, aware, able to think about these things and marvel at them. That is its own kind of miracle. Tonight, as you close your eyes, let the wonder of the earth's hidden depths fill your thoughts. Let the knowledge that you are standing on the thin skin of something vast and ancient bring you peace. The planet will continue its slow dance, long after we are gone, shaping itself, renewing itself, existing in a state of constant, gradual change. Beneath you, right now, the mantle is flowing. Currents of hot rock are rising from near the core, spreading out beneath the crust, cooling and sinking back down. This process has been happening for billions of years, and it will continue for billions more. The tectonic plates are moving, carrying the continents slowly across the surface, opening new oceans, closing old ones, building mountains and wearing them away. In the outer core, liquid iron is swirling in complex patterns, generating the magnetic field that protects us. And at the very center, the solid inner core spins, isolated and unchanging. A sphere of iron heated to temperatures we can barely imagine, yet held solid by the immense pressure of everything above it. All of this is happening right now, as you rest. The earth is not still, it is active, dynamic, alive with motion and energy. But that motion is slow, measured in centimeters per year, in degrees per million years. From our perspective, the earth seems eternal and unchanging, and in a sense, it is. The ground beneath you is solid and reliable. The cycles of day and night, the seasons, the climate, all continue with reassuring regularity. The earth provides stability, a home on which life can flourish. You have done enough for today. You have journeyed with me to the center of the earth and back, and now it is time to rest. The ground beneath you is solid, the air around you is calm. The planet continues its ancient rhythms, and you are safe upon its surface. Let your breathing slow. Let your thoughts settle. Let the warmth of the earth, radiating from deep below, be a gentle reminder that you are held, you are supported, you are home. The heat that warms the deep interior, the same heat that drives volcanoes and moves continents, is beneath you now, insulating you from the cold of space, keeping the planet's surface at a temperature where water can flow and life can thrive. Close your eyes. Feel the weight of your body sinking into the bed resting on the floor supported by the foundation anchored in the solid rock of the crust. And beneath the crust, all those layers we have explored, the flowing mantle, the liquid outer core, the solid inner core. They are all there, supporting everything above them, existing in a state of balance that has persisted for billions of years and will persist for billions more. Rest now. Dream freely. Let your mind wander where it will, knowing that when you wake, the earth will still be here, turning slowly through space, its interior warm and active, its surface cool and welcoming. You are part of this planet, and it is part of you. The atoms in your body have been on a journey through space and time, cycling through stars and planets, and they have come together, for a little while, to form you. One day, they will return to the earth to continue their journey. But for now, they are here, and so are you. Sleep peacefully. The earth holds you. The ground is solid beneath you. The magnetic field surrounds you. The warmth of the planet's interior radiates upward, keeping the surface at just the right temperature for life. Everything is as it should be. Close your eyes, rest, and dream.